All right, good morning. I hope yesterday's midterm went well. Today, we have to finish our chapter on related rates. We have a couple of examples we should do together, just in case we aren't quite sure when we look at the problem book on our own to know we have examples for each type of question. So the first one, we're going to look at two of them, the two remaining types. The first one, I'll zoom in here. I want to look at number 8. It's a typical one. Sand is piled onto a conical pile at the rate of 10 cubic meters per minute. The sand keeps spilling to the base of the cone so that the shape always has the same proportions. It's a cone, and the height of the cone is equal to the radius of the base. So the height is the same as the radius. So it's a pretty flat cone because the sand keeps falling and sliding down. Find the rate at which the height of the sand pile, the cone, increases when the height is 5 meters. So let's number this 11.8. So I want to picture a cone. So let's get a circle, a little flat circle for the base. And then the cone goes straight up to the center. Now my picture of the cone is much steeper than the question describes, because the question says the radius and the height is the same, but in some cases it might not be. In either way I need to know the radius and I need to keep track of the height. And what else do they care about? They care about the volume up here. The sand is piled onto the cone at a rate of 10 cubic meters per minute, which means the volume of sand, the volume of the cone, is increasing at some rate. So the volume plays a factor as well. So I also want the volume. So let's write our sentences to define what we're going to use. Let R and H represent the radius and height of the cone of the cone as we show with our diagram, and let V represent the volume. We're also going to need to know the volume, and that should be enough. So now we need to have an equation that relates these quantities, and it's going to be the volume formula for the cone. Well, you might not know what that volume formula is. It is a third pi r squared times h. And we have to remember this formula in case it comes up in a test or the final exam. So again, like the sliding ladder, like the expanding circle, we have some geometric formula that is our starting point. Now we need to get the related rates formula. For that, I'm going to use implicit differentiation, derivative, which is always a time derivative on the left, time derivative on the right, because all of these things, v, r, h, they're all functions of time. And they're all changing in some connected way as time changes. So if I want the rates of change, I need to take the time derivative throughout this equation. So the left-hand side is just dv dt, volume derivative. The right-hand side, I have two functions of time. I have this r function that is squared as well, and I have an h function, and they are multiplied together. So I am going to need a product rule here. So for simplicity, I like to just put all the constants with one of them. It might as well be r squared. And then I have my first and my second function being multiplied together. So the product rule then says it's the derivative of the first. Now I'm going to write this out so that we see all the detail. Derivative of the first, and we'll resolve that in a second, times the second, plus the first, times the derivative of the second. So I'm using the product rule. Let's scroll up a bit. So now let's do the second one first, because there's not much to do. The derivative of h, and h is just on its own, it's just dh dt. Whereas the first one, I have a function of a function, in that r is a function of time, and then that function is being squared. So I have to take the derivative of the outside function, which is the first part of the chain rule, which is going to be 2/3 pi r by the power rule, times the derivative of the inside function, which is r, so dr dt, and then I still have this h that was just waiting for the whole thing to be done. And then, of course, my plus in the middle. So I have a more involved related rates equation because the original had more functions of time in it. So there's my related rates equation. Now in this, let's see what we want and what we have at some point in time. So the process is the same as always. The equation just comes from a different place. So let's go back to the question and see what do we have. The volume is changing at a rate of 10 cubic meters per minute, so that's an increase. So that is the rate of change of the volume is 10. That's always the same. Then sand keeps spilling, the shape remains the same. The height of the cone is equal to the radius. So that is to keep things simple. The height is always equal to the radius. It's good to highlight that and see it. And we want to find the rate at which the height of the sand increases. So the rate of change of the height. So we want the rate of change of the height. So question mark. and we have the point in time when the height is 5 meters. So the height is going to be 5 meters. So in my related rates equation, I have a value for the VDT. I do have something for R. The RDT will have to C. I have something for H. I have something for R. The HDT is what I want. So I can only have one unknown in this related rates equation. So because my unknown is the HDT, I have to get numbers for everything else. So because the height and the radius are always the same, that means the radius at that point in time is also 5. So let's just see what can we do with the rate of change of the radius, because that's something we don't directly have a number for. And if I read the question, they do not talk about how the radius is changing in any way. But because the height and the radius is always the same, this also means that the rate of change of the radius will be the same as the rate of change of the height. So this is technically another question mark. So let's rewrite the related rates equation so that we can see where our unknowns are. So if I rewrite this first, I have my dv dt. I have 2/3 pi times r. Before I put numbers in, I'm going to be okay with r. I know r. dr dt, I'm going to swap with dh dt as my unknown. And then I have an h. Then plus 1/3 pi r squared. I'm going to have a number for that. And dh dt is the other, is still my unknown. So now that means I want to factor out the dh dt so that I have 2/3 pi r h plus 1/3 pi r squared equals dv dt. So then I have to solve for dh dt because that's my unknown. So dh dt, sorry, that almost looks like a V, hold on. dh dt is then dv dt over that whole bracket, 2/3 pi r h plus 1/3 pi r squared. And now I'm ready to fill in the numbers. So let's see now, what did we have? We had dv dt is 10, so 10 over 2/3 times pi times r is 5, h is also 5, plus 1/3 pi r squared is 5 squared, or 25, and that should give me my answer. So let's take out whatever calculator you may have and see what the answer is. I'll do it in the Discord chat if you want to see what that looks like. right, we get 0.1273 if we round to 4 decimal places. So it's positive, which means the height does increase, and we can write our concluding sentence as the height of the cone increases at a rate of approximately 0.1273 meters per minute. And we are done. Let me zoom out so you can see a little bit more of the question. Now, admittedly, this one is more involved because we started out with a more complicated geometric shape, having a more complicated volume formula and equation because I had a radius and a height. The derivative is more complicated, so everything is a little bit more complicated, but it follows the same steps and the same procedure as before. So there's one more to do just to cover almost all the shapes and formulas you need to know. And we'll look at 1114. Let me just make a new page before we read it. Eleven, 14. 14, not 4. There we go. All right. Where is it? It's another volume one. A spherical snowball is placed in the sun. The sun melts the snowball so that its radius decreases at 0.25 inches per hour. Find the rate of change of the volume at the instant the radius is 4 inches. Now this one is simpler than the cone we saw before, but it's just highlighting another volume formula we need to know. So I have a sphere and its volume is changing, so let's draw a picture and set that up. So we can have a little circle here. Nice and big. So let's suppose we have our sphere like that. We have a radius, and we're interested in volume. So we need to know the volume. Oh, first we need to find our variables. So let R and V represent the radius and volume of the sphere. Then, what is the volume of a sphere? Oopsie. Who remembers the volume formula for a sphere? Perhaps you do, perhaps you don't. Now is the time that you do. Let me just write volume first. The volume is 4 over 3 pi r cubed. So that is another one we have to know in case it comes up in a test question. Once I have my equation, it's very important because now everything is connected, is coming from that equation. So it's very important to have that equation and know these formulas. I then take the time derivative of both sides, implicit differentiation, in order to get rates of change in here. So I have dv dt on the left. Then I have the chain rule on the right because the radius is a function of time. and it's being cubed, so I have a function of a function. So when I take the derivative of the outside function, I get 4 pi r squared times the derivative of the inside function, which is dr dt. Here is my related rates equation. Sorry, my mic. There we go. Then, let me scroll up. We need to see at some point in time, they're giving me some extra information and asking me for something. What is that something? Sun melts the snowball, so its radius decreases at 0.25 inches per hour. So the rate of change of the radius, it's decreasing, so negative 0.25 inches per hour. Find the rate of change of the volume. So that's dV dt is what I'm looking for. And the radius at that moment in time is 4 inches. Now all the units are going to match, so I don't have to worry too much about that. When I look at my related rates equation, I see that I have information for everything except the one I'm looking for. So I already have the dV dt that I'm looking for solved and isolated on the left. I can just plug in everything. 4 times pi times 4 squared times negative. The radius was decreasing, right? Radius decreases, so the rate of change is therefore negative. So give my give my let me give myself more space here. So negative 0.25, and we're ready for our calculation. So we get negative 50.2655, I'll say. And we can write our concluding sentence. The volume of the snowball is decreasing at a rate of 50.2655 cubic inches per hour. Let me zoom out there. So we can see the whole question. It's a smaller one because our initial equation coming from the volume of a sphere was simpler. And then everything is a little bit simpler. But these are the basic ones we have to practice, and in the problem book there are more examples of them. Just one note, we're not going to do this one because it follows a very similar path to the volume of a sphere. But if we look at 1115, we have an ice cube and we have a cube as our shape. But I'm hoping that everyone can calculate the volume of a cube. In 1115, I'm not doing the whole one because we have to practice on our own eventually. In the volume of a cube, it's nice to visualize the cube. Whoop, that was the wrong line. Bad line. If I let the side length be x, they are all x. And the volume of the cube is going to be the area of the base. This is the base, which is a square, times the height. So it's going to be the side length cubed. So that is something that might come up as well, but it's hopefully not something that you actually need to memorize. That's one we would already know. So there are some formulas. Let's review them. Review the formulas we need to know. The two-dimensional ones are area of a circle. Area equals pi r squared. The triangle equation from Pythagoras. A squared plus b squared equals c squared. Then we have a cone. Let's clarify that. Volume of a cone. Volume of a cone, which is a third pi r squared. Then we have volume of a sphere, which is 4 over 3 pi r cubed. And then we have volume of a cube, which is side length cubed. Let me fix my P there. So those are all the formulas that you have to know to set up your related rates equations eventually. You have to take these equations, set them up according to whatever variables you defined, and then you have to do implicit differentiation on that in order to see what the related rates equation is. Now, as a side note, I want to go back and remember that we said, let me just zoom in here. Side note that we said the derivative of the natural log function for positive x is 1 over x. And we said that there are pros and cons to this. The pro is it's easy enough to memorize. The con is that we don't, at that stage, have the tools to explain why this is the derivative. But with implicit differentiation, we do. So we can now prove this. So let's start by saying y is equal to natural log of x. That's our function. Then, something I've emphasized many times, we have to be able, for convenience really, and this is one situation, to be able to switch back and forth between a log equation and an exponential equation. I can rewrite this log equation to e to the y equals x. And you have to go back and look at our discussion there if you're not sure. Essentially, what does this log mean as intuitively as possible? It represents the power of e that would give me an answer of x. Well, that's y. So e to the y would give me x. Now, we are going to do implicit differentiation, x is my variable, on this equation. On the left, I have, well, on the right first. Right is easy. Derivative of x with respect to x is 1. On the left, I have a chain rule situation because y is a function of x that I can't see in this version, and I take e to the power of that, so it's a function of a function. So the chain rule says take the derivative of the outside function e to the y with respect to y is e to the y. Times, says the chain rule, the derivative of the inside function, which is the derivative of y. Now, my goal here is to find dy dx, which represents the derivative we're looking for. So I'm going to solve for dy dx, and that's going to be 1 over e to the y. But e to the y, if you look a little further up, is equivalent to x, and we're done. And we've now proved by way of implicit differentiation that the derivative of natural log of x is 1 over x. Now I call it a side note because we just put it at the end of this chapter, but that doesn't mean it's not important. So yes, we memorized it. It felt a little unfulfilling to not know why. These two do not seem to be connected. The log function's rate of change function is a rational function. That seemed very strange. But we can prove it to show that it is. So that is the end of our chapter on implicit differentiation and related rates. Tomorrow we will go into the final portion of the course, and then we are almost at the end. Are there any questions before we finish the live stream of the function, of of this video? All right then.